Alex Mobaraki. I'm going to do a presentation on reverb. So, what is reverb? Reverb is essentially the sound of a room. It's the character of the room. The reverb sound is affected by the size and shape. So, what does it sound like? Well, if I clap my hands, you should be able to hear reverb. Yeah, that's good. You did. It's a less pronounced, delayed version of the initial sound. You mainly hear it in large rooms, churches, halls, maybe a cave even. It's most noticeable when the sound source is stopped, and then you hear the delayed sound. That is the reverb. How is it made? Well, all sound from the source projects outwards like a sphere, so in an omni way out from the source, and it reflects off the surfaces that it comes into contact with. When this happens, the initial sound hits the listener, and the other sounds that are going and hitting the surfaces are bouncing off at slightly delayed times because of the distances that are having to travel. Also, the sound waves lose energy as well, so that is why the sound doesn't just keep going on forever, it decays, it cuts. This is a diagram of what I just said. The middle arrow is the initial sound, and the listener hears it first. As you can tell, that arrow is a lot shorter, whereas the top and bottom arrows are longer, and those are the reverbs. And the time travelled makes it delayed. Okay. Reverberation time is the time required for the reflections of a direct sound to decay by 60 dB. You can see on the graph, you've got the sound level on the left-hand side, which is measured in dBs, and the bottom axis is time. And when the sound is turned off, with the arrow you can see, the point where the bend is, with the blue line, that's the decay, and then when it hits the 60 mark, that's when the reverb stops. Reverb time, essentially. Okay, this man is called Wallace Clements Sabine, as you can read. He was born June 13th, 1868, and he died January 10th, 1919, which is quite sad. He was a physics professor at Harvard University, and he was one of the first people that founded, the field of architectural acoustics. Interesting fact, he didn't actually have his PhD at the time of it. He kind of got landed with the project, and he figured it all out from there. He had to, he first set out to finding all the characteristics of the room, all the surfaces within it, for the lecture hall at Harvard, and he noted all the differences in the materials in the room. So with what he found, he listed for each frequency. So these are just some examples of some, but for wood, he gave, sorry about that. The ratings themselves go from 0 to 1, and 1 being fully, no sound being reflected, and 0 being all of the sound being reflected. So for example of something where all the sound would be reflected would be marble. Like a marble room, all of the materials are solid, hard, dense is important. Like, so those would be the lower ones. As you can see with brick on this table, unglazed is 0.03, that's quite a low Sabine rating. It's very reflective. Yeah, he named them all after himself, Sabine. Important thing, well, not an important thing, but quite an interesting fact, is that he did it all himself and with a portable wind chest and organ pipes, which is pretty cool, as the sound source. He used a stopwatch and his ears to measure it all. Yeah, he found that the reverberation time was proportional to the dimensions of the room and inversely proportional to the amount of absorption present. So this was his formula that he devised. It can be either done in feet or meters. If it's in feet, K is 0.049, and if it's done in meters, it's 0.161. V is volume of the room, so that's your width, length and height times together, and it's in meters cubed. A is the total absorption, which is the area of surfaces times by what we looked at before, its Sabine value at a given frequency. So here's an example of a room measuring 5 meters by 6 meters by 3 meters. The volume, like I said, width times length times height equals 19 meters cubed. Then to find the surfaces, you find the areas of them, so width times length, length times height, and width times height, and you've got those areas shown below. I've chosen the materials I had in the Sabine graph for each of my surfaces. So wood being the floor, beg your pardon. Wood being the ceiling, carpet on concrete as my floor, brick as walls, and I also have glass windows. With all of them taken into account, the surfaces coefficients equal 8.4 for 125 Hertz, and you look down, so the floor is 0.6, 0.45 for the walls on one wall, and where I've included glass windows, I've had to subtract their absorption value off of the walls area. It's important to include them. So looking at that, that is essentially my workings out. Once I add up all of the values, I have total absorption, and with that I divide the volume by the total absorption, which you can see on the right hand side. I'm going down in stages. So volume was 90 meters cubed divided by 125 Hertz total absorption, 12.26. The answer is 7.